What's going on, calculus students? Just want to share with you the thought process for this number 5 on the FTC problem solving. F is a function defined on the closed interval from 0 to 7. The graph of F consists of 4 line segments, okay, shown above, and G is this function that is an integral function. So before we even go into the finding of the answers, I'm just going to find the relationships here or spell them out. Since G is an integral function from 2 to x of f of t dt, which is this graph, G prime, which I know I'm going to have to access, is f of x from the fundamental theorem of calculus. Derivatives and integrals are inverses. I know I'm probably going to find either concavity or points of inflection, so I'm going to go further and go G double prime then is f prime of x. So this is the relationship that we kind of need to be flexible with, going backward and forward. So we're looking at this G function, which is an integral. So the graph of f, we're looking here at a derivative graph. So I say this is a derivative graph. Just to remind myself that places where the function is positive, that is increasing. G is increasing because its derivative is greater than 0. This part down here from 4 to 6, that's where G is decreasing because its derivative, also known as f, is less than 0. So I haven't even done any pieces yet, but that's kind of where your mind needs to go, because a long time ago we did this with polynomials. Now it's integral functions. So here's part A. Find G of 3. I'm just going to follow the rules here of what G is. It is the integral from 2, now 2 instead of x is 3, f of t dt. So I'm looking for, from 2 to 3, this area, which happens to be a trapezoid. So that's, I'm going to put notes here that this is trapezoid. And the area of a trapezoid is 1/2 the height, which in this case is 1, times the sum of the bases. And looks like that the highest one goes up to 4, lowest one, or that top one right there, is 2. So that's 6 divided by 2. Area is 3. Okay, I'm going to clean this up a little bit. Oop, get out of there. Whoop. Next part is G prime of 3. G prime of 3, oh, I'm on the same line here, that's nice, is the same as f of 3. So now our eyes go to the graph, but now we're not accumulating a function with an integral. We are just looking at f of 3. That is where x is 3, or where t is 3, I guess. That is 2. Input, output. And then the third thing we want is G double prime of 3. That is also known as f prime of 3. Now we look at that graph, our eyes go to it, but now we look for the slope of the tangent line at 3. Oh, so I shouldn't have erased that. I'm not looking at the value of the point, I'm looking at the slope. What is that slope? What is the rise over run? What are we looking at there? It's 2 over and 1 down, I think. That is 2. Rise over run, so that's actually plus 2 and minus 1, negative 1, sorry, negative 2. Wait, is that true? No, it's 0, let's see. It's f prime of 3, I think it's a negative 2, right? I'm sure you're screaming at me right now. I need to double check myself. That is that slope right there. We go over 1, down 1. Oh, I see. It's over 1, down 2. What am I thinking? That is -2. Woo! -2. Over 1 and down 2. Okay, part A, checked. Find the average rate of change of G on the interval. Average rate of change. My mind goes right to the this function. If it's the average rate of change between 3 and 0, I think of G of 3 minus G of 0 over 3 minus 0. And that means G of 3, I think this is the long way around. I think you could probably argue that this part up on top you could get to. I'm going to go the long way and say that's the integral from 2 to 3 of f of t dt minus the integral from 2 to 0 of f of t dt over 3. And now I'm just looking for from 2 to 3. Oh, we already found that. That's that region. That is 3 minus, now the integral from 2 to 0. We're going backwards. So that is this area here. But our length is -2. Our height is 4. That looks like 1/2 base times height would be, it would be normally 4, but that is now a -4 because our direction now of the length is -2. 3 minus -4 over 3, 7/3. For part B, let's see, give us some space here. Part C, for how many values C, where C is in between 0 and 3, is G prime of 3 equal to the average rate found in part B? For how many values of C is G prime of C equal to? So where is G prime of C equal to 7/3? Well, G prime of C, that's the derivative of our function. That's also known as f of C equals 7/3. And we have the function right up here. Let's look and see what inputs yield an output of 7/3. Our eyes go up and say, let's see, the input is going to be C and the output is 7/3. That's 2 1/3. That is right on this line. It looks like there are 2 of them, right? Where the function f, which is the derivative, intersects 7/3. We don't have to see exactly what they are, but we know there are 2 of them. There are 2 places where G prime of C equals 7/3. That was what it asked for. How many? We got it. Okay, wow. It's part D, we're almost there. Going to change colors here, and we go to find the x-coordinate of each point of inflection on the graph of the interval. Okay, so I'm going to zoom in on this function again, and I've erased some of them, but I'm going to put them back in there because there were places where G was increasing and places where G was decreasing. We look to the first derivative, which is this graph, and see if it's above the x-axis. That's where G is increasing. And where G is decreasing is where it's below the x-axis. The second layer that we want to look at is the second derivative test, or points of concavity. And that would be where the slope of tangent lines of this graph changes. So that means where the function, which is the derivative that we're looking at, changes from sloping, increasing to decreasing. this, and I'm making a separation here with this wavy blue line, that means we are concave up from this interval 0 to 2. The function now is decreasing until we reach 5. We are, and that means g is concave down, and then it goes back to concave up. So there look to be two different changes in concavity, also known as points of inflection, where concavity changes, and they occur at 2 and 5. So find the x-coordinate of each point of inflection and justify your answer. Because the derivative graph changes from increasing to decreasing, or vice versa, our points of inflection are x equals 2 and x equals 5, because these are the places where g double prime or f prime changes sign. All right, hope that helps. Live long and calculate hard.